Okay. So, today we shall discuss about inverters. Inverter, as the name implies, it basically produces a signal which is exactly opposite in phase with respect to the input signal, but as the problem, as in practical cases in most circuits, we deviate considerably from this ideal behavior. So, a measure of how good an inverter is typically judged by the difference in phase between the output and the input signal. If the output phase is exactly 180° away from the input signal, then we say that the inversion is perfect. Otherwise, we try to measure the amount of imperfection of the signal inversion. So, there are various configurations of the inverters, as we shall see. Okay. So, we find that, so we see the different configurations of inverters. The first one is basically the resistive load NMOS inverter, which is the simplest of its kind. The second one is basically the PMOS equivalent of it. It is a resistive load PMOS inverter. The third inverter shows a current source at the load, and it is called a current source load inverter. The fourth one is very popularly used and is called a CMOS push pull inverter. So, let us start with the CMOS, let us start with the resistive load NMOS inverter. Over here, as you can see, that it basically comprises of a resistance connected to the drain of the NMOS transistor. So, when Vin equal to 0, then this NMOS transistor is operating in the cutoff region, and since the NMOS transistor is operating in the cutoff region, current is not flowing to this resistive load, and therefore, since the current is not flowing, therefore, you get an output voltage that is equal to VDD. So, when Vin equal to 0, V out equal to VDD. Now you start increasing Vin. So, when Vin greater than Vt, current flows through resistance Rd, and therefore, you can see that V out starts, there is a drop occurring across the resistance Rd, and you can say that V out starts falling from VDD. Now, you go on But what is the region in which this MOS transistor will be operating? It will be operating in the saturation region, because now the V out is V out is basically VDD minus RD. Now, when current starts flowing, initially this ID is very small, therefore, V out is close to VDD, and as you go so V out is very close to VDD. So, you can say that V in minus V in is minus ground is greater than V out, sorry, V out is greater than V in minus VT. So long this condition is satisfied, this MOS transistor will be operating in the saturation region, and when V out becomes equal to V in minus VT, the MOS transistor goes deep into the active region or triode region. So, in which region should we operate the MOS transistor if we want to get a good gain out of this inverter? Obviously, since the transconductance of the MOS transistor is maximum in the saturation region, therefore, we will operate it in the saturation region. In the active region, the transconductance falls sharply, and therefore, we should avoid going deep into the triode region. Now, this inverter I should discuss separately, because this is very important, because we are using a constant current source as load instead of this passive resistance. So, we can write, since this is a constant current source, therefore, we can write dID equal to 0. Now, ID is a function of VDS and VGS. Therefore, dID equals to del F VDS VGS del VGS at constant VDS into delta VGS plus del F VDS VGS del VDS at constant VGS into delta VDS. Since this is equal to 0, I can now this term I can write now. Let us do the substitutions. Del F VDS VGS del VGS, I replace it by GM, and del F VDS VGS del VDS I refer to as GDS. So, therefore, we can write this equation as GM. Now, see, this delta VGS is a small signal change in the value of this VGS. I can write it as small VGS plus GDS into VDS equal to 0, which implies, since dID equal to 0. So, this implies VDS by VGS equal to minus GM by GDS, so which I called the gain AV. So this basically indicates the gain of the inverting amplifier, and it's a function and it's dependent both on the GM and GDS, and therefore we can draw the small signal model like this. For the current source load inverting amplifier. So this is called the transconductance of the MOS transistor, and this is called the output resistance of the MOS transistor. Coming to the CMOS push-pull inverter, you can see that an NMOS pull-up transistor and a PMOS pull-down transistor are connected in cascade, and this configuration is called a push-pull configuration. So when Vin equal to 0, this transistor is operating in the cutoff region and this transistor is operating in the active region, and therefore Vout is connected to ground through this NMOS transistor, and as you increase Vin, as soon as Vin exceeds the threshold voltage, this NMOS transistor starts conducting, and therefore current starts flowing through this series combination of NMOS and PMOS transistors, and as a result Vout starts falling from VDD. Then a stage comes when both these two transistors are operating in the saturation region. After that, this when you give a value of Vin such that this Vin becomes greater than VDD plus mod VT, this PMOS transistor goes to the cutoff region. So in essence, the output characteristics of the MOS transistor, NMOS and PMOS transistors connected as a push-pull inverter, becomes something like this. In fact, this is the inverting amplifier that gives the best possible response amongst all the different types of inverting amplifiers studied so far. In this CMOS push-pull inverter, we can see that the current basically flows through the cascade connection of this NMOS and PMOS transistors and down to the ground. Now over here we can see that this is the region at which we can see a sharp change in the output with respect to the input, which means the gain is very high in this region. So one of the most important things about this circuit is that this is used both as a digital and an analog circuit. So in this region that is to the left of this dotted line and to the right of this dotted line, you can see the output voltage hardly changes with the input, and we use it as digital circuits in these two regions. The region in the middle, that is between the two dotted lines, you can see that a sharp change in the output with respect to the input, and we use the circuit as an analog circuit in this region. So it is one of the most popularly used amplifier circuits, and is also serves as the building block of most of the analog circuits. So it is popularly used in various applications.